Hey folks, welcome back. In this video we're going to go over a one-worked example to show you how to do problems involving the charge to mass ratio for electrons, and this is our fourth application of fields. Now if you haven't already done so, check out my previous video covering the theory on this topic, and that way you can apply what you learned in that video to this one. So let's get into it. Now in our one and only example it says, in an experiment to measure the charge to mass ratio for an electron beam is fired between parallel plates in a vacuum tube. The vacuum tube is placed between a pair of Helmholtz coils. Part A says crossed electric and magnetic fields are applied to produce an undeflected beam. The current I in the Helmholtz coils is measured to be 0.31 amps. The potential difference V across the plates is 1200 volts. Part 1 says to show that the velocity V of the electrons between the plates is given by lowercase v equals capital V over BD, where D is the plate separation and B is the magnetic induction. Well, we can say here that for the undeflected beam, we have that the magnetic force must equal the electric force. So we can insert the equations for these, QVB equals QE. And you'll see we can cancel a Q from both sides, and that leaves us with VB equals E. So to get V on its own, we can divide both sides by B to get V equals E over B. And then from the relationship sheet, we have the potential difference is equal to electric field strength times distance, and therefore rearranging for E, we can divide both sides by D to get E equals V over D, and that means we can replace this E in this expression here with V over D. So we end up with V equals V over BD, which is the equation we're asked to derive. A part 2 says the magnetic induction B is given by B equals 9 times 10 to the minus 7 Ni over A, where N the number of turns is 320 and A the effective radius of the coils is 0.073 meters. Calculate the magnetic induction B. Well, we're going to use this equation and just sub in the numbers here. So we have B is what we're trying to find, N is 320, I is 0.31 amps, and A is 0.073 meters. So writing down our equation here, we have B equals 9 times 10 to the minus 7 Ni over A. Substituting in the numbers gives us 9 times 10 to the minus 7 times 320 times 0.31 divided by 0.073. And putting that into your calculator should give you an answer of 1.2 times 10 to the minus 3 Tesla. A part 3 says the plate separation D is 0.045 meters. Calculate the magnitude of the velocity of the electrons. Well, we can use the equation that we derived in part 1. So here we're trying to find the velocity V. We know the potential difference capital V is 1200 volts. We know the magnetic induction B is 1.2 times 10 to the minus 3 Tesla that we just calculated in part 2. And the plate separation D is 0.045 meters. So writing down our equation from part 1, we have V equals V over BD. Substituting in the numbers gives 1200 divided by 1.2 times 10 to the minus 3 times 0.045, and putting that into your calculator should give you an answer of 2.2 times 10 to the 7 meters per second. Lastly, part B says the electric field is switched off and the above magnetic field only is applied. A deflection Y of 0.015 meters is measured. Show that Q over M equals V over RB squared D, where the symbols have their usual meaning. Or in other words, this is the charge to mass ratio Q over M. Well, we can start by saying that the magnetic force provides a centripetal force here. So equating the two expressions, we have QVB for the magnetic force is equal to mv squared over r for the centripetal force. And here we can cancel a v from both sides to get QB equals mv over r. And then what we could do here is cross multiply, so if you do that you get QBR is equal to mv, and then to get Q over M on its own we can divide both sides by the mass, so we end up with Q over M on this side is equal to V over RB on this side. But you might also be able to see that from this step, so to get the M on the denominator on this side we need to divide both sides by M, and then to get rid of this B from this side we need to divide both sides by B. So we get that Q over M equals V over RB, and remember we want to get it into this form here where that's capital V on the top for potential difference. So we can then rewrite this right hand side by saying Q over M equals E over RB squared. And we can write that since V equals E over B for an undeflected beam. So we've just replaced the V here with E over B. And that's why we've now got an E in the top and this B in the bottom becomes B squared. Now we're getting closer to this expression because we've now got RB squared in the bottom, but we also want to get rid of this E now. Now we can rewrite this now as our final answer Q over M equals V over RB squared D, where we've used the expression for electric field strength E equals V over D. So we've replaced the E on the numerator with V over D so that it becomes V over RB squared D. And that's the equation we were asked to derive. That's all for this video folks, thanks for watching. If you made it to the end I really appreciate it. Make sure to give the video a like, subscribe to the channel, and I'll see you in the next one. Take care.